Good evening, everybody, and thanks so much for taking your Friday night to spend it with me. Hopefully, I can tell you a little something about the place that we all live and do it with a certain lightness, because it is Friday evening after all. The Basin Range, or the Great Basin, the physiographic province, is the product of tectonic stretching of the North American plate. Stretching or extension results in faulting within the plate, normal faulting, and that's well reflected by the digital topography at almost any scale across the Great Basin, where the extension appears as a series of valleys, basins, and ranges that are on either side of the fault. So for example, let's see if we can point here. The Steens Mountain is one famous normal fault in which the west side is one block of the fault and the Alvord Desert side is the other block of the fault. In regions that are undergoing continental extension, they get wider in time. If you sat on the Wasatch Mountains, for example, in Utah, and you waited long enough, you would see the Sierra Nevada move west or away from you over time. The Northwestern Basin Range, which is going to be what I'm going to talk about tonight, is controlled by a style of deformation which is actually unique to the Pacific Northwest. And my goal, if I achieve it, I'll be happy, is to show you that how the evolution of the northwest corner of the Basin Range is linked to that deformation field in both space and time. Now, I'm certain, I'm confident, but cautiously so, that we all are on the same page about the plate tectonics of the Pacific Northwest, but I think a short primer will help seed the discussion that I'm going to show you tonight. So as is widely known, and because the Great Oregon Shakeout was just earlier this week, and the focus in shakeout in the Northwest is the plate interface between the downgoing Juan de Fuca plate and the North American plate, the so-called Cascadia subduction zone. The North American plate, however, is not inert. It's not just sitting there waiting for Cascadia subduction zone earthquakes to occur. It's in fact a broad region of deformation. This is a map from a paper by Gene Humphreys at the U of O, which shows how the modern deformation field manifests itself in North America. So if you have a purple color over here, you're essentially not deforming. And if you have a light color, as we see over here on the west, you're moving relative to North America in a northwesterly direction. And that change in deformation rate is highest across the San Andreas Fault, where there is right lateral shear, as everyone knows. But when you get up to the Cascadia area, the edge of North America is defined by the Cascadia subduction zone, as I mentioned a moment ago. And in terms of the strength or the resistance of these plate boundaries to deformation, the North American plate, the Cascadia subduction zone is actually pretty weak. And so the arrows that we see here, which are showing the relative motion of positions within the North American plate, moving to the northwest towards the Cascadia subduction zone, actually are the plates actually are allowed to move freely westward. And the net result of that a weak boundary to the deformation field in the North American plate is this crazy plot right here. Yeah. This is a map of the geodetic velocity field of stations in and around the Pacific Northwest relative to stable North America. So what you're seeing here is, of course, geography. Here's Oregon, Washington, the borders right here. And what each one of these points represents is the relative motion of one station with respect to another one. So if you have a small arrow that's within this ellipse, the station is essentially not moving relative to its neighbors. But by the time you get out to, for example, Newport, which is about here, you are moving at about 10 to 12 millimeters per year. And what these data show is that if you go from Southern Oregon to Washington, you're in fact spinning around a vertical axis whose pole lies somewhere over here in the Oregon, Washington, Idaho border region. And thus, the way the North American plate is deforming internally in the Northwest is fundamentally driven by this vertical axis rotation. And I'll return to this point in a minute. The second part of North America that's important to know about is the composition or the major pieces of blocks that make up the North American plate. And the most famous was the subject of your field trip earlier this summer, the Silesia Train, or it's also called the Oregon Coast Block. It's sometimes called the Siletz River Volcanics. It has many names, but nonetheless, it's a giant piece of ocean lithosphere that was accreted to North America about 50 million years ago. And it forms a large block between the subduction zone on the west and the volcanoes of the high Cascades on the east. This block is part of North America, and it is moving within this rotational velocity field. On top of Silesia, and especially at the boundary between the Basin Range province in the east and the forearc or the Silesia Train in the west, are a series of magmatic belts that are also familiar to us because they include the major stratovolcanoes of the Cascades, like Mount Hood, Mount Jefferson, Three Sisters, etc. The volcanic rocks that make up the Cascades are most commonly lumped into two belts on the basis of age. There's the Western Cascades, which is the older and earlier part of the Cascade volcanic history, and it extends in time from about 40 to roughly 7 million years ago, at which time the so-called high Cascades are become the locus of volcanism, and the major stratovolcanoes are built in the period after about 7 million years ago. And I mention this because these volcanic rocks are sitting right astride the boundary between this Siletz block on the forearc and the extensional province here in the back arc. So I assume that Ray Wells has already done his turn here, giving his Friday night seminar. So this will be a review that is on the quiz. I think I heard someone laugh. That's good. This is Ray's figure, and he has a little, if you haven't had him, you got to get him back, or if you have had him, get him back. He has a little graphic that he moves with scissors like a puppet. But in that block rotation apparatus of his, the Oregon Coast Block in the south moves west and northerly, and in the intermediate part of the belt moves northerly, and by the time you get up north, it's moving towards the northwest because it too is moving around this pole of rotation in the vertical axis deformation field. And you can see that Eastern Oregon lies in the wake of this rotating block. So what does that mean? That means that if you're a fault within this vertical axis deformation field, you have a sense of motion and a rate of motion that depends on your distance from the pole. So your velocity depends on how far you are away and where you are within that rotating velocity field. So let's just take this fault in the lower part of the figure, red fault with a northwest orientation. The instantaneous velocity on that fault is shown by the schematic velocity diagram, in which it's showing both a direction and a magnitude. But the key point is that at this point, the relative motion across that fault should be to the northwest, and we should get some sort of oblique normal faulting on that structure. If I go up the arc now, the arc of the velocity field, and I put a fault in that has a more northerly orientation such as this, you can see that that fault nearly parallels the instantaneous velocity at that point, and thus that fault should be experiencing essentially pure strike slip faulting, or mostly strike slip faulting with a small amount of extension. And then if I continue up the arc here, and I embed another fault with a different orientation, you can see that in this case, the relative velocity, the instantaneous velocity at the fault should be one in which there is contraction or reverse faulting on that fault. And this general concept is what we're going to explore tonight, but we're going to mainly focus here on the southerly part of this diagram. The manifestation of that northwest is that the Oregon coast block is swinging outward, northward, and inward as you go from south to north. And in the region behind the volcanic arc, which is indicated by all these orange dots, we have a number of important structural provinces that are well known to all of us. For example, the Yakima Fold Belt. And I'm not going to really say very much about this tonight, but it's widely thought that the fold belt exists because the relative velocity, or the velocity of deformation in the northern part of Oregon and southern Washington is expected to be contraction or shortening. In the southern part, where the relative velocity is northwesterly, we have extension, and that is the Basin Range structural province to the west of, or east of, let's say, Bend, Oregon, all the way out here to Burns. And in the south, we have a more complicated structural style known as the Walker Lane province, which includes both northwesterly trending faults and north trending faults. So this is a region of mixed normal and strike slip faulting. By the time you get to Bend, however, you notice the vector is rotating more northerly and nearly parallel to structures within the region of Sisters, Oregon. And this is a transition region between extension and contraction up to the north. So I'm going to basically outline the history of extension here and then talk about, in particular, how this western edge of the boundary is related to the Oregon coast block. I think there might be a question in the chat. Yeah, oh, that's generic. Okay, I'm just doing bookkeeping here. Sorry, everybody. So one of the realities of the Zoom era, you just start talking to yourself and sharing your innermost thoughts with the rest of the crowd. All right, so get back on track here. Here's what we're going to do. I'm going to give you a two-part talk that, first of all, is going to describe how the Basin Range opened in the northwestern corner in both space and time. And then I'm going to turn to the question of the western edge of the Basin Range and ask, how is it linked to this Oregon block, the Silesia block? How does the back arc, what's happening in the back arc, relate to what is happening in the forearc? So if you're not on the flight to Burns, I strongly suggest you get off the plane now. All right, everybody. Baldwin had it right. I don't know why you're listening to me. I was concerned, of course, that everybody had read The Geology of Oregon by Baldwin. This is the old version I read in high school, but it has this beautiful block diagram which explains the basic story with some things that are going to be revised in a more contemporary way. But the basic idea that Baldwin is showing here is that if you're in the southern part of the Basin Range, it's more extended. And by the time you get to the northern part up here by Burns, Brothers, or Bend, the Basin Range extension diminishes to effectively zero, and it's limited at the north end by the Brothers Fault Zone. And you can see that the topography actually reflects that basic history, and Baldwin himself must have considered the topography of Oregon when he created that block diagram, because when you're in the southern part of the Basin Range, you see very large ranges and very low basins. And as you go to the north, for example, across the Surprise Valley up through Lake Abert, in this area up here, you see that the height of the block that's on one side of the fault is getting lower and lower and lower. And by the time you get to the Brothers Fault Zone, it's so muted as to not even being able to see it as a topographic feature. And so there must be something important about the change in topographic expression, both in the east to west direction and the north to south direction, because all of these ranges have a more pronounced topographic expression in the south and a muted topographic expression as you go farther to the north. So what we're going to do here to address the where and when is to show you a quasi east to west transect from some work that my student did out here near Crane, Oregon, which is the site of Oregon's only public boarding school, the Crane High School. Then look at work of another student who worked in the Lake Abert area for his PhD dissertation, and then revive a very old set of papers by Gary Smith, who constrained the age of faulting here on the westernmost edge in the Green Ridge area. So the structural style of the Basin Range, it's not as exciting as it is in Nevada, let's just put it that way, because the magnitude of extension is not very large. What you see here in Oregon are steeply dipping normal faults where the basin side moves down relative to the range side. And there is very modest tilt of the blocks. Here is the Summer Lake Basin, in which the units are almost not tilted at all. Lake Abert, however, there is a strong easterly tilt to the basin block relative to the Abert rim on the other side. So Oregon Basin Range is characterized by steep faults, modest extension, and modest amounts of tilt. But that tilt, oh boy, I just got the spinning wheel of death. Sheila, can you still hear me?
Yeah.
Okay, I am going to do something ill-advised, which is to stop sharing and see if I can figure out if I can get this started again. Sorry, everybody.
It's okay. I didn't notice any glitch at all.
You didn't?
No.
Okay.
Did anybody else? They're all saying
Looks
it's
good.
okay. Yeah.
Looks
Okay,
good.
Hi, Scott. Okay, let's give this another shot. Let's see. Sorry about this.
It's okay.
Yeah. Okay. How are we doing now? Are we seeing,
Looks good.
hopefully we're seeing the Eastern Basin Range, Crane Basin. Is that the slide everybody sees?
Yes.
All right. So the point here is that when a block is tilted, that actually allows for stratigraphy and volcanic rocks to accumulate and record via angular unconformities when they moved. So if you look out in the Crane Basin, this is now to the east of Burns, Oregon. This is a typical footwall block of a normal fault within the Crane Basin. The bedrock is the Steens basalt, and it's overlain by volcanic clastic rocks and some of the key ignimbrites of Eastern Oregon, like, for example, the Divine Canyon tuff, or in this case, the 7.25 million-year-old drinkwater basalt. But what these rocks show is that the Divine Canyon is more steeply tilted than the drinkwater, and the Steens is more steeply tilted than the Divine Canyon, which is a set of angular relationships that shows that this basin formed sometime shortly after Steen's basalt was erupted and was moving progressively up through about 7 million years, accumulating a thicker section next to the bounding fault, which is in white in the photo and black in the cross section below, and onlapping onto the neighboring block of the neighboring fault. So this is a relatively old structure by Oregon standards. Similarly, when you go to the west to Abert Rim, or the Lake Abert Basin, you have volcanic stratigraphy that includes a series of basalts of different ages. TBA, for example, here is an 8.5 or so million-year-old unit that dips steeply to the east. If you go to the footwall block of this basin, you see that TBA has an angular unconformity with a younger basalt, TOB, which is about 1 million years younger, and thus the onset of the extension across the Abert Rim area must be bracketed by the angular unconformity as sometime between 8.7 and 7.7 million years ago. When you hit the Cascades, you hit the land of Gary Smith and all the other students of Ed Taylor, Rick Connery, the whole crew. I can't even remember all their names. But Smith's cross-section captures what happened quite nicely, and that is that there is an asymmetric and east-westerly thickening package of rocks in the so-called Deschutes Basin that's 7.5 to 4 million years old. And by the time you're under the high Cascades, this unit is of the same age, but is considerably thicker and is isolated, or that faulting isolates this high Cascades region from the neighboring Deschutes Basin after about 5.5 million years, because the units, the volcanic rocks and the volcaniclastic rocks of the high Cascades were not making it into the easterly Deschutes Basin. In a neighboring drainage in the Upper Mackenzie, there was a continental seismic profile shot in the mid 1980s as part of the big cohort program that was run out of Cornell University, and that profile that came right up the Mackenzie River, Highway 126 out to Bend, showed that the Pliocene and Pleistocene rocks to the east of the from the high Cascades to the east formed also a wedge-shaped set of stratigraphic units that thickened towards this bounding fault, which separates the high Cascades from the western Cascades. And so in the Cascade Range, we see the western edge of the Basin Range and these constraints, both the stratigraphic constraints of Gary Smith and the wedge shape as clearly depicted in the Cocorp line, show that this is a basin which was growing after about 7.5 million years, just a little bit after the onset of extension in the Lake Abert region. So this is my obligatory super busy slide. What I showed you was my student Justin's work out here in the Crane Basin that shows that extension started after 15.5, then in the Lake Abert area after 7.5, and then Gary Smith's work up here after 7.5, showing a pattern of migration of extension to the west. But if you consider other data around the region, for example, Jenda Johnson's master's thesis on the northwest flank of Steen's Mountain, she has stratigraphic evidence for extension after 11 million years. Ray Wells had a work he did in the southern part of, I think, the Hart Mountain area, or the Hart Wildlife Refuge, that showed that extension was younger than 15.5 million years. And so you get a pattern that emerges where Basin Range extension is earliest in the east and in the south, and grows northward and westward with time. The one exception to that is George Priest's work down here in the Klamath Basin, which shows that at least for faults in this set of faults to the west of the Klamath Graben are younger than 4.5 million years old. So another way to do this is just to make a pretty map that tries to synthesize that westerly growth or onset of extension from the Steens Mountain region, including the Crane Basin, to the Cascade Arc over a period of about 8 million years, from 15 to 7 million years. And once you know that, and you know that it both propagated to the west and grew to the north, the topography begins to make sense. The more extended southerly part of the Basin Range is indicative of the longer period of time over which extension has occurred, and the younger ages and more muted expression of the Basin Range as we go to the north and to the west reflect the northerly growth and shorter period of time over which that extension has occurred. And we could even extend that to thinking about Nevada, where there's the most pronounced Basin Range topography, and contrast quite significantly with Oregon as also reflecting a greater amount of extension, in part because it's been happening for a greater period of time. Now, the northern edge of the Basin Range is a tough place to work because there are so many faults and it's very poorly exposed. But I had a student named Dave Trench who seemingly liked to drive around in the dust. And he worked on the transition between the Basin and Range, which are expressed by some of the major faults here, Winter Rim, Avert Rim, Hart Mountain, and so forth, and asked the question, how does the Basin and Range end at the Brothers Fault Zone? Because this is the other major boundary of the Basin and Range in Oregon. This map is pretty hard to digest, I acknowledge that, but basically the thing that I want to draw your attention to is that the main Basin and Range faults trend to the north, and the main Brothers faults have northwesterly trend. And in this map, I've color coded them in terms of the amount of throw. So if I'm thick, dark line, I have a lot of throw. And if I'm a thin dash line, I have a little amount of throw. If I'm a solid line, I am dipping to the west. And if I'm a dash line, I'm dipping to the northeast. And I point that out because you can look at a series of cross sections that go from the northernmost edge of the Basin Range into the Brothers Fault Zone from the top to the bottom, where the faults are color coded according to their dip directions. So in this case, a solid fault is dipping west, a dash fault is dipping northeasterly. And what you see is a handoff or a diminishment of the amount of slip from the Basin Range into the Brothers Fault Zone over a relatively close spatial scale that goes from about a couple hundred meters of extension in the north to effectively zero by the time you hit the Brothers Fault Zone. Although there is an expression there, the magnitude of extension is very small, and thus essentially quantifying what I showed you in Baldwin's diagram, that the northern edge of the Basin Range is really defined by a slip gradient on Basin and Range normal faults, which go to zero by the time you reach the Brothers Fault Zone. Now, this extension has made springs, et cetera, but it just hasn't done that much work on North American crust. What you see at the top here is a simplified
Is anybody else experiencing?
Yeah, at first I thought he was just buffering, but he's all frozen up.
He's frozen.
Okay. Let's see. It may work better if everybody turns their cameras off, and that I've heard that helps. Let's try that. Andrew, can you?
Andrew, you're muted now,
Yeah.
and now we're seeing your slides again.
Okay, welcome back, everybody, I hope.
Yes,
If the Zoom era has done anything, it's made us all maybe a little more patient.
yeah.
Okay, can you
I-
see a picture with a big brown cross section at the top?
Yes.
Something about the low velocity zone.
LVZ.
Perfect. What this is a crustal profile showing the surface and the moho. So this is North American crust. And what you see is that the moho is elevated underneath the Basin Range, as would be expected in crustal extension. And in the bottom part of this, I've taken that elevated moho and the average surface at the top just to show that when you thin the crust, as we've done here, here's, let's say, the Owyhee Plateau with normal or pre-extensional crustal thickness. When you thin it, the magnitude of extension is reflected by the amount of elevation of the moho and the degree to which topography has been lowered. And from that, you can make a ballpark estimate of how much extension you expect, which is about 15 kilometers across the Basin Range. If we add up all the normal faults, we get about 5% of that from the Cascade Arc to the Owyhee Plateau, which means that something else must be accommodating that extension. And one possibility is diking throughout the across the province, which is not really a radical thought given the widespread and continuous amount of basaltic volcanism that has been associated with extension throughout its history. And so we get a magnitude of extension which is less than what we expect, and that drives the inference that the missing amount of thinning may be explained by diking that we can't see or quantify as readily as we can the amount of thinning that has occurred by normal faulting across the Basin Range. And I'm going to turn to this western edge question now, I think. Let's see. Yeah, all right. So the western edge of the Basin Range is really quite interesting because this is the place where the Oregon Coast Block, which is over here underneath the Willamette Valley and the Western Cascades, is separating from the eastern side of the state, or the Basin Range province itself. And so what I'm going to do is show you a series of studies that my students have done from Klamath Falls up through the Sisters Fault Zone to try to understand what is the magnitude and style of deformation as we go from south to north. One thing that is relevant to this question is basically, where are the faults? This map shows black faults and red faults. Red faults are just ones that my students have used the Dogami LiDAR database to refine, revise, and improve. And there's no difference between those two. But if you made a plot, as we did over here on the right-hand side, of just the density of faults per area, what you see is that the most dense faulting is actually occurring to the west of the magmatic arc, which is lying right about through here. Here's Newberry, such as up here. This is the Lapine Graben and so forth. Crater Lake, you can see quite clearly. But what this is showing is that the current faulting is actually most dense far to the east of the main arc of the Cascades. So if we start in the Klamath Basin, this is a photo of Klamath Lake from Hammaker Mountain to the southwest of Klamath Falls. And it just shows the most spectacular example of normal faulting that you can see almost in the state outside of Steens Mountain. Here's a tilt block. There's a normal fault right here. It's exposed at the range front on Highway 97, and the block tilts backwards to the east. And here's another normal fault right here, also exposed, on Highway 97, and the tilt block is back to the east. So this is clearly a place where there is considerable normal faulting, but it's not the only style of faulting, because the Klamath Basin lies at the northern end of a region of distributed right lateral shear. Right lateral shear is indicated here by these arrows in this figure from Rick Blakely's work, where the right-hand side is moving southwest, the southeast and the left-hand side or the west side is moving northwest. And what he posited and what the geology reflects is that northwest trending faults have right lateral shear, north trending faults have extension on them. And thus the Klamath Basin is at the northern end of this Walker Lane that extends all the way down into California along the east side of the Sierra Nevada. The Klamath Falls earthquakes actually showed how the kinematics of faulting works in the Klamath basins. The main shocks, the ones that caused the damage and the 2 deaths, were localized on the Lake of the Woods fault, where the earthquake epicenters, because the faults dip, are off to the east. And without going into detail, the seismological method of showing the kind of displacement in a earthquake is given by a beach ball. And when the beach ball has a dark exterior and a light interior, it's indicative of normal faulting. When the beach ball has a checkered pattern, as is shown by these 3 aftershocks, that is indicative of strike slip faulting on either a northwest or a northeast oriented plane. If the northwest plane is the one that generated the earthquake, a checkered beach ball like this is indicative of right lateral faulting on a steeply dipping fault. And so the importance of this is that if you look at the geology, and LIDAR is the reason that we can make this kind of map that I'm about to show you, this fault right here, which we're terming the Howard Bay Fault, has very clear evidence of right lateral strike slip faulting on it, whereas these faults in the West Klamath Fault Zone have almost pure dip slip motion. And that's what I'm going to show you right now. Here's a bare earth LIDAR image, and I assume that everyone knows what this is, but Dogami has developed a phenomenal public resource of topographic data wherein the LIDAR is a reflection of the elevation of the Earth's surface as measured by a laser, and the resolution of those data are so high that you can see very delicate features like little streams in this post-glacial fan that's flowing into southern Klamath Lake. But the key point here is that in places like at Site B here, streams that are crossing the Howard Bay Fault come down, step right, and flow out. All 3 of these streams show a right lateral offset in a quaternary fan that is almost certainly correlative with moraines coming from the mountains that are last glacial maximum, or about 20,000-ish years old in age. So this is an active right lateral fault with a small amount of normal displacement and northwest trending. But when you go around the corner and up to the north on the North Klamath, or on the West Klamath Lakes Fault, the moraines of the same age, like QGO, for example, here, is offset by normal faults with down to the east motion. And the crest of those moraines show almost no lateral displacement at all. The magnitude of displacement on a profile such as this black line right here is about 20 or so meters in the last 20 million years or 20,000 years. And in a profile in the canyon bottom in sediments that are younger than the moraines themselves, the scarps are in the neighborhood of 1 meter, 1 to 1.5 meter high. So this is an active fault system with almost pure dip slip motion on it. As we go to the north from Klamath Lake and we reach the Chumult region, there's a graben there that's widely known, the Chumult Graben. The east side of that is formed by a topographic feature known as Walker Rim, and it's a place where faulting goes from north trending to northeast trending. And in this undergraduate student thesis that my student Katie Alexander did, she mapped the structures and dated a few of the lava flows across here. And I draw your attention to this 4.5 million year old lava flow here that is displaced vertically about 325 meters across the Walker Rim fault zone. And the reason why that's interesting is that first of all is a fairly large degree of topographic relief. And the Walker Rim fault zone projects directly, here's Walker Rim, and Katie's work is right up over here. It projects directly under and into the Newberry, the flank of Newberry volcano. So here in the south end of the Walker Rim fault zone, there's about 300 meters of relief or so, topographic relief across the fault, which means the fault displacement is larger than that. And that fault system projects up to Newberry. Well, in the work of Ken Light and Marshall Gannett in this paper about water resources in the Lapine Basin and Deschutes Basin, they showed that there's almost 400 meters of quaternary sediment. That section thickens towards the Walker Rim fault zone. And so there's very good evidence that the Walker Rim fault zone is actually bounding this fault basin. That's not particularly new, but it also means that the fault zone is projecting directly under Newberry itself, which implies that Newberry must be faulted and must be sitting astride a fairly large Basin Range fault. Of course, with no vertical exaggeration, it doesn't look that impressive. So the vertical exaggeration amplifies the several hundred meters of relief in Walker Rim fault zone that I projected and modified Ken Light and Marshall Gannett's cross section to show that the Walker Rim fault almost certainly underlies the flank of Newberry volcano. The other thing that's really interesting about this part of the world is this fault zone right over here, which cuts the Deschutes River, or is in the Deschutes River basin. On the west side of the Lapine Basin, LIDAR data shows that there is a very clear fault scarp. Here, the topography is rendered as a slope shade map, wherein the coloring shows is proportionate to the angle of the slope. In this case, this fault dips to the west. The sloped side of this scarp is showing a facing to the east. I just said west, but crucially, it also shows lateral displacement. Here, this edge where this river terrace comes in to the fault is picked up again up over here. So there's right lateral and normal displacement across this fault, which is bounding the west side of the Lapine Graben. And like the West Klamath Fault Zone, if you do profiles across terraces of different age, like for example, if you compare one in T1 to a profile across an older surface like T3 here, what you see is that there is a difference in the vertical and lateral displacement as a function of the age. This surface here, T1, shows a vertical separation of about 1.5 meters and a lateral displacement of 6.5 meters, a very strong strike slip component of displacement on that fault zone. As you continue north from Newberry, here's Newberry down over here in a geologic map. It's well known that the Sisters Fault Zone has a strongly north-northwest trend and extends right down through and includes the Lava Butte volcanic center where it crosses Highway 99. But the fault zone, like the Walker Rim Fault Zone, disappears when you come underneath the flank of Newberry, emerges, and then projects to the north up towards Black Butte and then up towards the Mount Jefferson area, showing that, as on the right-hand side in a gravity anomaly map, that the Sisters Fault Zone is actually cross-cutting the older Deschutes Basin here, as shown by these blue rocks, and extends right up into the Mount Jefferson region. That is also an active fault zone with less constraints on its activity because it's such a distributed sense of shear. But the important part of this story is really in the region from Black Butte up towards Mount Jefferson, in which the fault scarps are present on northwesterly trending faults, but are not present on things like the Green Ridge Fault, which is the earlier formed normal fault system. So the Sisters Fault Zone is cross-cutting the Deschutes Basin, cross-cuts the Green Ridge Fault, and extends into the Mount Jefferson region. And if we look in this part of the world right over here, oh, shoot, got ahead of myself, everybody, sorry about that. We can say something about how old the fault zone might be by comparing the vertical component of displacement across lava flows of different ages. So from left to right, we have a 400,000, 150,000 and 100,000 year old lava flows with topo profiles across them. And if you look at the magnitude of the vertical displacement as a function of age, these two have comparable amounts of displacement, whereas the 100,000-year-old flow has a relatively smaller amount of displacement. Now, they're not moving very fast, but these data suggest that the Sisters Fault Zone is relatively youthful in comparison to features such as the Green Ridge. By the time you get up to the Mount Jefferson region, so here's Black Butte, Green Ridge, and Mount Jefferson up here. If you look at this valley up here, the LiDAR data are just incredible. They show, for example, this lava flow, which flowed down into glacial topography, which was undoubtedly cut and last occupied at the last glacial maximum. But this flow is younger than that because it's flowing into that valley and is cut by this fault zone here. And there's plenty of evidence that faults in the axis of the arc are active and are offsetting Quaternary and Younger features. Here's a 3D rendering of looking from the north to the south of LiDAR data. Here's the White Branch Valley, which is the one that goes up through Mackenzie Pass. This is Belknap Crater up here for those of you who know this part of the world. The road from Sisters down to Highway 126 comes right down through here. But what you see here that's important are all of these faults in what's being called the White Branch Fault Zone, which cross-cuts glacial topography and lava flows that are both within the White Branch Valley and on the shoulder to the northeast. So these are active faults permeating the Cascade Arc. And they lead to a view, at least in my opinion, that there is a fault zone that extends from the Klamath Basin through the Walker Rim area underneath Newberry and then comes out of the Sisters Fault Zone that is in effect slicing off a piece of the back arc and adding it to the fore-arc block. In addition to that, the fault zone is interesting, or the pattern of faulting is interesting in so much as in the south, faulting is limited at the arc itself. Here's Crater Lake, and the faults of the Lake of the Woods zone do not cross Mount McLaughlin, for example. But by the time you get up to the Mount Jefferson area, there's some indication that faulting is actually crossing from the east to the west side of the arc. And I'm hoping that the newly acquired LiDAR data for this part of the world, which has always been a hole in the Dogami data set, will reveal the nature of that faulting and will be a test of the degree to which the Sisters Fault Zone is actually crossing the arc at approximately the latitude of Mount Jefferson. But by drawing this line in here, of course, I've biased your view, or I've biased you against my views, hopefully biased your view into thinking that basically the active faulting has now added a piece of the back arc region onto the western block, the Oregon Coast Range block. So what that might look like is in a standard cross section, we might have Juan de Fuca going down underneath the North American plate, with the Oregon Coast block forming the basement to the Western Cascades, and the Basin Range basically continuing all the way to the western side of the High Cascades. In the view that I'm putting forward, I'm suggesting that this region of the High Cascades, at least from Mount Jefferson to the south to the Klamath Basin, is in fact moving with the Oregon Coast Range block. Structural processes have in effect added a piece of the back arc and the arc itself onto the Oregon coast block and are now moving, which would now be moving with the Oregon coast block independently of the Oregon Basin Range. A second implication of what I'm telling you here is that if the extension has a high magnitude as we approach the Cascade Arc, it means that the Oregon coast block is in fact in footwall of a big normal fault. And that might provide one explanation for something that Rick Connery and other people noticed quite a long time ago. And that is that intercanyon lava flows that are of 6 million year age and younger that cross from the Western Cascades into the Willamette Valley have this uplift, unexplained uplift across the Western Cascades. And this should say roughly 700 meters. I'm not sure what happened to my graphic here, but nonetheless, at its peak value, the differential elevation between the old 6 million year old ridge capping basalt and the modern stream is as much as 700 meters. Well, that deflection is most likely being driven by uplift of the footwall block across the breakaway between the Basin Range faults and the Western Cascade or Oregon Coast Range block. So a second implication, which is more subtle, but nonetheless important from the point of view of how the landscape has been developing, is that the limit of Basin Range extension near the Cascade Arc is allowing for uplift of the footwall block. What's interesting about that uplift, however, is that if you measure the amount of missing material across the Western Cascades since the eruption of these ridge capping basalts, about half or a little less than half of that uplift can be driven entirely from erosional removal of material and the flexural response of the crust to getting thinner by erosion on the west side or on within the Western Cascades. And maybe if I haven't spoiled this and I get invited back, I can describe all the work we've been doing to try to understand the erosional and uplift history of the Western Cascades. Okay, so it's almost time for my beer. I think many of you already have yours. The extension story is east to west over a period between about 15 and 7 million years from the Crane Basin or the Steens Mountain area to the Cascade Arc. It's distributed regionally by 7 million years and at a low rate, and it is accumulating additional displacement in the south and growing to the north over that time period. In the south, that means Klamath Falls area, up through, let's say, roughly Crater Lake. The extension is limited or ends at the arc. But by the time we get to Newberry and north of there is northwest directed transtension as reflected by the Sisters Fault Zone that almost certainly is not limited by the arc, but in fact crosses the arc. And as a result of that pattern of deformation, there is an active addition of material to the edge of the Oregon block or the Siletz terrain that is occurring because the faulting is localized to the east of the volcanic arc, and that material to the west of where that faulting is occurring, it could be thought of as in fact moving now with the Oregon Coast Range block, and thus helping to explain how that block can move wider and add material from one side of the arc to the other. So as I promised Sheila, one other thing you've got to mention here is the fine print. No, I can't take much credit. There are a lot of people who worked on this. Everybody with an underline under there is a student. Almost all of them were OSU students who did an undergraduate master's or a PhD thesis working with me. And it's really their hard work and blood, sweat, and of course tears that led to a lot of the ideas that I presented today. I did promise Sheila that I was going to make a shameless plug for our own lecture series. The Thomas Condon Lecture is an annual lecture that's been going on since the late 1940s. This year is a friend of all of ours, Jim O'Connor, will be the speaker. And if you want to attend the lecture, you can see it in person on Wednesdays, November 3rd on campus here at Oregon State, or you can go to the College of Earth, Ocean, Atmospheric Sciences webpage and search for the Thomas Condon Lecture, and there's a place to register for the Zoom if you'd like to watch it. So with that, next time you're on top of Paulina Peak, you can think of me and think of Anita Grunder over there left, who's telling you she's heading north on the Oregon block. And I greatly appreciate you having me.
Thank you. That was fantastic. That was very good.
Should
Very
I
interesting. Thank
I
you.
think I'll stop sharing.
That was really good. Really appreciated all the background that you gave with it too.
Yeah, so Sheila, I'm going to go ahead and start with the questions here.
Yes, thank you, Carol.
So yeah, thank you, Dr. Meigs. Those were great images and pictures that really complemented your talk. I'm going to start back up at the beginning when questions started rolling in. So Deepika asks, why do we have those faults? Is it due to rotation, or are they pre-existing before the rotation began?
Oh, thanks for asking that question. What do you think I should share my presentation again, or should I just I'll do a Scott Burns and just gesticulate madly? I think I'll show the slides. Do it, Burns.
We trust your judgment here. You do what you think is best.
Well, the answer is that the majority of the faults, as far as I can understand, are probably new faults, and they're forming largely because of the stress field, the rotation, and the fact that there is the crust is getting weaker because of the thermal regime underneath from thinning itself. The one exception to that is the Walker Rim fault zone, which is my favorite one of all of them because it trends northeast. It is the only fault zone in Eastern Oregon which does that. And if you look at a map, what you see when you cross the arc is you drop straight into the Klamath province where everything is northeast trending. The basement behind Silesia is almost certainly the old Mesozoic rocks of the Klamath, which extend across the state up through Mitchell, which I know also the OSU field camp started about the same time as the Geological Society of the Oregon Country in the mid 1930s. But that is the only fault zone that trends northwest, and I bet you anything, it is in fact a reactivation of, in some fashion, of older Mesozoic faults, which are at depth and undoubtedly project directly in the deeper part of the crust across the arc towards the northeast into northeastern Oregon.
All right. So Wes was asking about, he was mentioning that the LiDAR image of the Northwest and Basin Range area is wonderful. Is it available to non-professionals? And then Clark magically provided that to people in the chat. If you want to bring that up, people can click on it.
Those data, you can find those data in at least 3 different places. You can get sort of downscaled version from the Dogami LiDAR viewer. Oregon State has a copy of all of the data, but it's in a fairly cryptic format. And then the last place is that Dogami gives all of its data to a data distribution website called Open Topography, which has LiDAR data from all around the country that is contributed to it. So there's at least 3 different ways that one gets their hand on any LiDAR data from the state of Oregon.
All right, and then he follows up and asks, before LiDAR, was geological evaluation more difficult? Has LiDAR revealed geological features that would otherwise still be a mystery? RE, the Basin and Range area.
I saw Scott gave a double thumbs. I think that was because he wants to bring back air photo. Or reveals the land surface in ways that we never thought possible. You know, the Gales Creek Fault, which is out there in the Forest Grove area, was essentially not known as an active fault till LiDAR came along. But in the Klamath Basin, for example, this fellow named Hawkins did a fabulous air photo interpretation of the exact same area that we have LiDAR now for, and he recognized and intuited the nature and rate of faulting that more modern techniques using LiDAR data simply refine. But to some greater or lesser extent, air photos in the old days worked, and if you were a good interpreter, they were good. But there's well, Jim O'Connor, he probably is going to get mad at me for taking his expression, but he calls LiDAR the crack cocaine for geomorphology. Once you've had some, you cannot stop getting it.
That's good.
That's great. Charlie asks, what influence of the melting of the subducted Juan de Fuca plate have on the faulting? Would the rising of the melted plate also cause extension?
Everybody who's a petrologist can just try to mute me right now because I'm about to say something heretical. Basically, my feeling is that the localization of the stratovolcanoes and most of the magmatism is actually structurally controlled, and that's really what's driving where things are. So it is contributing to it, I suppose, in so much as it's causing a thermal change in the thermal structure of the crust. But the degree to which it is actually controlling where faulting is occurring, I think is debated. Like I have a nice photo of that Dillman Meadows fault that is in Katie Alexander's master's thesis, where she shows that it goes from a very clear fault that cuts terraces of multiple ages, it's a tectonic structure, straight into the Bachelor volcanic chain. So if you're away from the Bachelor volcanic chain, it's a tectonic fault, and then it turns into basically a conduit for a bunch of monogenetic cinder cones. And so in that case, that's a really beautiful example, at least in my mind, of a fault which is controlling where magmatism is occurring as opposed to the inverse, where the magmatism controls where the faulting occurs. And I would also, this is also somewhat heretical. Maybe only in my mind is it a bad thing to say in public, but I believe Newberry basically to be at a step over. It has to be fault controlled. There's just no, there's the map pattern and the information about the nature of faulting away from where Newberry is so clear cut that I just can't imagine that it is not fundamentally a function of the intersection of the Sisters fault zone and the Walker Rim fault zone.
And it's always been an enigma where, is it related to the Cascade? People have said, is it related to the Cascades? I think it's related to the high lava plains. It's never really fit in. That kind of explains some of that.
It's a beautiful weirdo.
Yeah.
Yeah, I just remember when I lived in Africa, a large part of Angola is sitting on a big plume. A large part of Africa is sitting on a plume, and it's pushing up Angola, and you're getting a lot of the faults and the Fish River Canyon and stuff. A hike to there. So anyway, cool.
Okay, so Carol Hassenberg has a question. I've heard it posited that the North American plate boundary is shifting from the San Andreas fault to the Walker Lane. Do you think that is what's going on here?
I don't it's hard to say. They're especially if you talk to people from the University of Nevada, Reno. This one fellow who's super smart named Jim Faulds. That's his story. But at the present time, San Andreas is taking up 80% of the plate motion, and thus if it's happening, it's certainly not giving it up very fast. But I don't know that we're actually seeing that. You know, the Walker Lane, John Dillis worked on it. He's an OSU professor in northwestern Nevada. Is about an 11-million-year-old feature. So it's not happening very quickly if that is happening. Distributed deformation is the normal mode of deformation of plates that have continental crust. And you can just rattle off the examples one after another. The one famous one is the India-Asia collision, where you have the Himalaya, you have the Tibetan Plateau, and then behind it there are huge strike slip faults like the Altentog Fault that are moving at a very high rate. The Andes is another example. You have the subduction zone on the west, and you have to go almost 1,000 kilometers to the east until you get away from active faulting. So if you have a continental plate, you have distributed deformation, and how it reorganizes itself in time is probably mostly related to how plates move with respect to one another rather than something happening in terms.